Hello there, Mr. Sutton here, bringing you this lesson on interval of convergence. In this one, we're going to find both the radius and interval of convergence for a series. To start our discussion, let's say that we have a Taylor power series for some function, where we have x minus a to the n and c of n, that's all the coefficients that we got with the factorials and the derivatives at all orders of whatever this function was. All right, so we could ask the question, at what x values does this series converge? And this is an important question because there are some series, like, for example, this series that I have to model the sine function, that as you increase the number of terms, we'll see that this series gets closer and closer to the function in question. And there are other series, such as this series I made on Desmos to model this rational function, where as you add more and more terms, it doesn't really seem to matter. You just can't get past a certain point on the function. So it's helpful to know when you create an approximating polynomial for a function, am I dealing with this situation here, like sine, or this other situation, like 1 over 1 plus x, which is a very limited range of numbers that are going to converge. So in general, we're talking about here the interval of convergence, or IOC for short. This is the set of x values where a series will converge. So given a series, there is some range of x values within which, if we plug in an x value in this range, our polynomial is going to come pretty close to whatever the true value of the function is. Now, this interval of convergence has a center. It's this a value right here that we use to create the series. So we have a center at a, and we have perfect knowledge at a. Like, we built this series with the information, the function values, the derivatives at a. So our series is always going to converge at that center. But now, our interval of convergence also has two endpoints, here and here, where the series may converge or may diverge. We don't really know which until we run some more tests. So one other thing we can talk about with this stuff is something called the radius of convergence, which I'll call ROC for short. This is the distance from your center to your endpoints. So this distance right here in this direction or in the other direction. Now, the handy thing about the radius of convergence is if we know that we're plugging in some x value to our function, where the distance between x and the center, the absolute distance, is less than this radius, like this x value here, then we know that that x value will make our series converge. And if we plug in some x value, like this one over here, whose distance from the center is bigger than the radius of convergence, then we know the series for sure will diverge. We'll start things off with a little bit of reasoning about convergence. Let's say we have some series S that converges at x equals 6 and diverges at x equals 8. Which of these has to be true? And it could be more than one of them. So pause the video and see if you can figure out where this thing has to converge or diverge. All right, so my reasoning on this, I always start on these problems by writing down what I know to be true for a fact. So here's a fact. The center of this thing is x equals -2 because we have x minus 2 here. Let's write it down. I'm also going to write down what I definitely know about convergence. So to do this, I'm going to see how far I had to go out to get a converging point. We went out to x equals 6. There's a distance of 4 to get from 2 to 6. That means that I'm guaranteed that within 4 of x equals 2, I'm going to be converging. Anything that's closer than this point to x equals 2 is going to have to converge. So I can say I converge for sure between -2 and +6. And I can also write that I converge for sure at +6, well, because they told me so. -2, though, I can't be sure about that, because if that's an endpoint, I might be diverging there. Where can I definitely say that I diverge? Well, if I have a diverging point out at 8, that means that anything that's further out than 8 in either direction is going to diverge. So I'm guaranteed, and this is a distance of now 6 between x equals 2 and x equals 8, I'm guaranteed that I'm diverging for anything that's less than -4, because that's 6 out from 2 in the negative direction, and anything further out than 8 in the positive direction is also going to diverge. And again, I'm going to include 8 because they actually gave me that one. Going through all of these now, S converges at x equals -1. -1 is between -2 and 6, so it must converge. It's closer than the converging point that they gave us. -2 is right on the border, and since they didn't give us that we converged at -2, that's ambiguous. That means we can't choose it yet. We'd need more information. x equals -4 diverging now. Well, that's right on the border between possibly converging and diverging. Again, we can't conclude we're diverging because we might be converging there at that border. And then finally, diverging at -5. Well, -5 is further out than the point that they said diverged earlier. So -5 definitely has to diverge. We're going to move forward in this one by finding the radius and interval of convergence for this series right here. So what kind of series is this? Well, you might have noticed that each of these has an exponential term here. So this is really just one big geometric series. What's the common ratio here? Well, it's the thing that we're multiplying by over and over again. So we have a -1, we have a 7x minus 2 squared, because this is really squared to the n power, and then we have a 9 in the denominator. So this is our common ratio right here. So to find the radius of conversion, we're going to start by setting up a situation where a geometric series would actually converge, namely where the common ratio absolute value is less than 1. So that'll be our starting point. We'll start by setting our common ratio absolute value less than 1. Now, when I do this, I don't really need this negative here because it's inside absolute value anyway. So I'll just say absolute value 7x minus 2 squared over 9 is less than 1. Now, to actually find the radius of convergence, we have to put this thing in the following format. So we have to put it in 1x minus a form. It's okay if there's something being added or subtracted inside the absolute value, but the x value needs to have a coefficient of 1. So to do this, we're going to start on this one by multiplying both sides by 9. So I'll bring a 9 over here. And now I have to take the square root of both sides. Now, when you do this, if you're not used to using algebra with absolute value inequalities, I mean, normally you would have a plus or minus 3, but you can't really write the absolute value if something is less than a negative, because absolute value is always positive. So you really just need the positive root here, which is 3. Next, we're going to just get the x here to have a 1 next to it. To do that, we have to divide everything by 7. So I'll have x minus 2 over 7 less than 3 over 7, and I'm keeping the absolute value around. At this point, now that I've got this in 1x minus a less than r form, the radius of convergence is just going to be the r value, whatever's on the other side of the absolute value, which in this case is 3 over 7. Now, to find the interval of convergence, we're going to just solve this inequality we wrote with absolute value of r less than 1 for x. So you could start all the way back here if you didn't need to find the radius of convergence in the first place, if they just wanted the IOC. But since we already did a bunch of work to find the radius of convergence, I'm actually going to start us off at this point in the problem. So we're just going to use this absolute value inequality for my interval of convergence. Now, remember, when you're solving an absolute value inequality like this, you can rewrite this without absolute value by putting the stuff inside here between the negative and positive version of this 3/7. So we can write negative 3/7 is less than the stuff inside, x minus 2/7, which itself is less than 3/7. And now I just have to isolate x by adding this 2/7 everywhere. So we have negative 3 plus 2 is negative 1/7 on the left side. We have just x in between now. And over here, adding 2/7, we get 5/7. So this then is our interval of convergence. Now, we said that the series may or may not converge at the endpoints here. So in general, these less thans could also be less than or equals. We don't really know for certain in every situation. But the nice thing about a geometric series, you never need to test for convergence when you're using your geometric test endpoints. Because we know for certain that if the common ratio is less than 1, there's no ambiguity, the series will converge. For this next example, we're trying to find radius and interval of convergence for this series. Now this one you might notice is not geometric. It's close, but this n over here kind of messes things up because it's not an exponential part. So for radius of convergence, if your series is not geometric, we're going to use the ratio test instead. So instead of doing common ratio less than 1, we're going to do the nth ratio, the n plus 1 term over the nth term, absolute value less than 1. Pause the video and start setting up that ratio test. All right, so we should end up with limit as n approaches infinity of the n plus 1th over the nth term. N plus 1th term, we're going to have an n plus 1 instead of n. We'll have x plus 3 to the n plus 1, 5 to the n plus 1. And now that's all the n plus 1th term up there. So downstairs, inside this huge fraction, we just have all this stuff, which is just the nth term altogether. Doing my little multiply by the reciprocal trick, I've got my numerator, which has an n plus 1 and x plus 3 to the n plus 1, and this 5n, which is flipping upstairs. In the denominator, I've got the 5 to the n plus 1 and all of this stuff down here, the n and the x plus 3 to the n. Now I need to reduce this a little bit so I can more easily take the limit. The 5 and the 5 to the n plus 1, those are going to cancel, leaving me with just a 5 in the denominator. Upstairs, the x plus 3 to the n plus 1 and the x plus 3 to the n also cancel a bit, leaving me with an x plus 3 in the numerator. And this n plus 1, as n approaches infinity, I can ignore this plus 1, so I'm just going to call this n. So in my numerator then, I've got an n, and I've got an x plus 3 to the n plus 1. Or just x plus 3, actually. The n plus 1 canceled when I subtracted the exponent of n. In the denominator, what do I have left there? Well, I had a 5, I had an n, and this whole x plus 3 to the n is just gone. Now you might be wondering why I didn't also get rid of this plus 3 that's with the x. So in general, as n approaches infinity in these problems, x is treated as a constant, and we have to keep anything that's being added or subtracted to x around 2, because this is all one big coefficient on n. So now when I take the limit as n approaches infinity, I can actually cancel out these n's, and I just end up with x plus 3, which again is a constant, over 5. I still have that inside absolute value, and now just like I said I was going to do up here, I'm going to take this nth ratio and set it less than 1. Okay, time to solve now. I almost have this in the form I need for the radius of convergence, but I still need to multiply both sides by 5, so that'll give me a 5 over on the right side. And now this is in 1x minus a form, so that means our common ratio is just this number over here of 5. Now for the interval of convergence, I'm going to solve this absolute value inequality, so I'm going to write negative 5 less than x plus 3 less than 5, just like we did before, and subtracting 3 from everywhere, I've got negative 8 less than x less than 2. Or do I? So this is one of those situations where, since you did not use the geometric series test, since you used the ratio test instead, you always need to test for convergence at the ratio test endpoints. So we're going to continue this problem and see if this series converges specifically at negative 8 and 2. So we're picking up where we left off on that last example. We had a rough draft of our interval of convergence between negative 8 and 2, and we're trying to figure out if we converge at these endpoints to see if either of these inequalities should have an equals under them. So to get this process going, we're going to plug each of these endpoints, negative 8 and 2, in for x in the original series, and then figure out if the resulting series converges or diverges. So let's say we plug in negative 8 to start us off. So that would be negative 8 plus 3, which is negative 5, and negative 5 to the n over 5 to the n, that's really like having negative 1 to the n. So this is really the sum of negative 1 to the n times n. Well, applying my nth term test, because I always do that first, I see that as n goes to infinity, this is going to go to positive or negative infinity. It just keeps growing in both directions. Since that's not 0, we can say that this endpoint diverges by the nth term test. All right, let's try the other endpoint out, positive 2. If I plug 2 in for x, that's going to be 5 to the n over 5 to the n, which is just 1. And we have an n left over here. So this is really just the summation, if I plug in x equals 2, of n. Well, if I take the limit of that as n goes to infinity, well, n goes to infinity. So that means, since that's not 0, this one also diverges by the nth term test. At this point, we're going to write our final interval of convergence to reflect whether or not we converged at the endpoints. Since we did not converge at either of them, these are both going to remain less than rather than writing less than or equals to. So I'm going to have negative 8 is less than x, which is less than 2. For our last couple examples, we're going to take a look at some oddball cases. Now normally, when you use the ratio test on a series, you end up with an absolute value that has an x inside that you can then go ahead and solve for. But what if you did all of that craziness with the n plus 1 and nth term and ended up with 0? What would that mean in terms of your interval of convergence? Well, the ratio test, we're always comparing things to 1. If your result is less than 1, then you pass the ratio test. But in this case, passing means that our series is passing the ratio test for all x values. Well, if all x values pass, that means our interval of convergence, the place where the x values make this converge, is just going to be all real numbers. If everyone passes, then everyone's included. So for this one, we would write an interval convergence of negative infinity less than x less than infinity. And you could even talk about the radius of convergence of this thing being infinity, because that's how far you're going in both directions. For this next one, if you get infinity as a result, well, anything bigger than 1 is going to fail the ratio test. So this is a big fail right here. If the series fails the ratio test for all of the x values, that means your interval of convergence, it's not nothing, but it is just going to be the center. Remember, the center always converges for a series. So in this case, our interval of convergence would be whatever a is. So we could say x equals a is that one. The radius of convergence in this situation would then be 0, since you're going a distance of 0 out from the center. This concludes our lesson on intervals of convergence. Till next time, Mr. Sutton signing off.